Okay, so section 4 and 5 together, and it's about waves in the electromagnetic spectrum. So it says fill the gaps in below. So I've taught you red, well, please work pen, red monkeys, insert vultures under xylophones. Great. Draw a line, we know they're all ionizing and cause cancer because they knock electrons out of atoms. So radio we've got, so that one must be micro, and infrared visible, UV or ultraviolet, and then gamma at the end. Please make sure you know that, and that's going from long waves to shorter waves. Shorter wavelength waves. Okay, state which region matches the use. So detected by the human eye, well, it's clearly got to be visible. Used to sterilize water or detect bank forged notes, ultraviolet. Treating cancer, told you about the gamma knife and told you a story about my friend. Mobile phones, please make sure you know this, it comes up a lot, that's microwaves. And detected by aerials for communication, think at the top of the Rekin where we have a radio mast. What is a transverse wave? So I've taught you get a T, make a right angle, so that's perpendicular, and we've got V, P, D, O, E, T. So the vibration is perpendicular to the direction of the energy transfer. Right, so it says state where the following are transverse or longitudinal. I'm going to give you a tip. If you know that sound is longitudinal, everything else is transverse, pretty much. All right, so X-rays, that's light, transverse. Sound, longitudinal. And just remember that, sound is longitudinal. Water, transverse. Microwaves, transverse. So it makes it really easy. Just remember, sound is longitudinal. Everything else we're going to go for is transverse. And most of the time, that'll be right. Okay, below is the trace for a sound wave. It says, what is the amplitude? So the amplitude is half the height. So I can read up here, there's half the height to that point there, and we can see it's 2. So 2 meters. What is the wavelength? Now I got this wrong in class because I read each of the squares. So I'm going to pick here, and then I'm going to go 1 square, 2 square, 3 square, 4 square, 5 square, 6 square. But can you see each square is half a meter? So I'm not going to do it by squares. I'm now going to do it by meters. So every 2 squares is 1 meter. 1, 2, 3, and then I've got it. So that's 3 meters. What increases if the sound gets louder? So increasing the amplitude makes it louder. Squeezing the waves together increases the pitch. So, for example, that would be quiet. That is a loud scream, but at least you get this idea. Bunching together, higher pitch, stretched out, lower pitch. So it says, what increases if the sound gets louder? It is the waves get higher, so it is the amplitude. And we could get that from this bit here. What changes if the sound becomes higher pitch? There's 2 ways of answering this. So imagine that's a normal wave. If it was to get higher pitched, it'd do that. So the wavelength has got shorter or decreased, or we could say the frequency has increased. Next one, we've got the wave equation, always comes up. Foxes stab wolves, and it says, what is the frequency F? So we can see F equals S over W. So pull down the speed, 330, pull down the wavelength, 2.25, and we get 146.7 hertz. Make sure you know the frequency is hertz. Okay, next part. You're going to love this. This is the same speed equation, except for rather than a ramp, we've got a boy chucking rocks into a pond. So a boy throws a stone into the pond. Explain how we could try to practically find out the speed of the water waves. Oh, there we go. Shoot Donald Trump. I need a ruler and a stop clock. There we go, and we're away. Use a ruler to measure a distance in the pond. Time a ripple to cover that distance with a stop clock. Speed equals distance divided by time. So you can imagine I'm going to mark a distance here. I'm going to put in his hand, there's his rock, he's a naughty boy, he's trying to kill ducks. Let's put a stop clock in his hand there, or floating on his shoulder. And what you can see is, well, when this ripple here comes across, I'll do it slow-mo. So here it comes, start, stop, and that would be the speed. All right. How would a duck move when the ripples pass by? Well, we know we're moving the energy, we're not moving the particles, so the duck would just bob up and down. All right. But try to make sure that your arrow is lovely and straight. So the duck would bob up and down. And that's that section done.